Hello and welcome. I'm really glad to see so many people joined and came here to listen to my talk. My name is Igor Maravic, and I'm a software engineer working in Spotify. I've been with Spotify for almost 4 years, which is an eternity for one software engineer. For the past 2 years, I've been working in a team which is maintaining and developing Spotify's reliable event delivery system. Before that, I was also an infrastructure engineer, and I was working on maintaining and developing Spotify gateways. In my free time, I like to travel, and in many places I go, people find me quite interesting, and in some of the places, they're not really afraid to show it, as you can see here in the picture. But yeah, enough about me. Let's talk a bit about Spotify. Spotify is a service which aims to provide all of the music of the world to its customers at the tip of their fingers. It is ubiquitous. It's available for mobile, it's available for web, desktop, PlayStation, cars, many different connected speakers, pretty much everywhere. A big distinguishing feature for Spotify in the beginning was the content it has, and also the instant playback that the users would feel once they press a play button. But as the time went on, this was not enough. In order to stay on the top, Spotify needed to start innovating. This is why, at some point, Spotify started investing a lot of features built on top of big data. So here are a few of my favorite features. So we have your release radar. This is a customized playlist which comes customized for each user and contains the new release songs that the user is most probably going to like based on its listening habits. Then we have fresh finds. Fresh finds are the set of playlists which are trying to predict where the music industry or the music is going to go in the next few months or maybe years. We can actually do that by tracking the listening habits of the users which are marked as hipsters. Seriously, and this is not something that I read internally in Spotify. This was actually a news article that I actually figured out that we have a new feature, and then it was giving me an explanation how do we do that. And finally, my favorite feature so far, and favorite feature of many of the Spotify users, is Discover Weekly. What Discover Weekly does, it actually comes with the music that the user is most probably going to like based on its listening habits. It comes fresh every week. Most of the times, this is the only playlist I listen during the whole week. And also one fun fact, one of the Spotify, my colleagues, actually came and said this is a conspiracy by Spotify, because by providing this and by providing you a good recommendation, Spotify can actually tell you what to listen. And, well, it seems like it's happening. But those are the cool features that we used data to produce. But what is more important is that the data is also used for producing a core feature of Spotify, which is one of the pillars on which the Spotify is built. In order to stay legal, Spotify is paying a certain amount of money for each of the stream which is generated to the music right holders. This amount of money which is being paid is called a royalty. As the Spotify grew, as the number of users grew, we can see more listening hours, and then you can actually see on the graph, this is the amount of royalties we are paying across the time. What the recommendation features and the royalty calculations have in common is that they are being powered by data which is collected from the Spotify clients. And all of that data is being delivered by Spotify event delivery system. But these two are not the only two features which are powered by our data. We have many more other features. So the data is also used for the business intelligence teams. It's also used to run our A/B tests, also do the crash reporting. And then if you've been to the Kirchhoff talk, you can actually also see it's being used to track the ad clicks. the star of today's talk is going to be the Spotify's reliable event delivery system. I'm not going to go that much into the low-level architecture details on how the system is built, but I'm rather going to give you a high-level overview on what our Spotify, or what our event delivery system needs to do and why. I also focus on some of the key operational aspects of the system. How do we do monitoring? How do we scale the system? And then finally, how do we do the testing? Let's start with the high-level overview. Most of the data we're having is being collected from the Spotify clients. Whenever a user action occurs, an event can be generated. So for example, we have an event which is being generated once the user starts listening to a song. We have another event generated when the user stops listening to a song. We have an event when it subscribes to a playlist, unsubscribes to a playlist, and finally clicks on an ad. All in all, there is more than 250 unique event types which are being generated from our clients. We expect this number to grow even further as we work on making the instrumentation more approachable to the Spotify developers. Many of these events are actually varying in different dimensions. We have some events which are small as few bytes, and then some events which actually have the messages which are as big as few kilobytes. We have events which are being generated sporadically during the day, and we have some other events which are being generated 200,000 times per second in the peak hours globally. And also, events are varying on the loss requirements they're having. Many events are okay with occasional loss, but some events, like the events which are used in the royalty calculations, are having strict no-loss requirements. But beside, oh, what happened? Come on. But beside our event delivery system needing to take care of different event types flowing through the system, it also needs to deal with the sheer load of messages which is being generated by 100 million monthly active users that we have today. In order to be able to iterate faster on our system and also to scale it easily, we decided to use as many Google Cloud components as we could. So instead of Kafka, we're using Cloud PubSub. To save state, we're using Cloud SQL and Data Store. To manage infrastructure, we're using Compute Engine. All the data that we're delivering is always delivered to the cloud storage, and it can also be delivered to the BigQuery. Our event delivery system needs to deliver all the events into the hourly buckets. What the hourly bucket means depends on the storage implementation to which we deliver data. So in case of the cloud storage, an hourly bucket is a folder, the same thing in the case when we deliver data to Hadoop. In case of BigQuery, it's a table, and in case of Hive, it's a partition. One thing that I like to point out here is that events are being destined to a bucket or determined to which bucket they belong to based on the timestamp when they were received by our system and not on the timestamp when they were generated by our clients. This might sound a bit of counterintuitive, but the fact is that by doing this, we can guarantee the timeliness of data delivery, and we can also guarantee that we can guarantee with a high enough confidence that all the events which are destined to a specific bucket for a specific hour are going to be delivered to that bucket. Timeliness is also an important aspect of our event delivery system. The raw events which we delivering are being used potentially by a chain of data jobs. In case we are having delays, we're creating more delays for our customers, which in turn generates even more delays for their customers. This is why we internally have a timeliness SLA that we expose to our clients, and we have a process that we follow in case the data is delayed, and we have a process of how to communicate this with our customers. In order to keep up with the SLAs, we need to have our system running 24/7. Interesting to note here is that the Spotify is a bit different from other big companies. We don't have a operations team like Uber or Google or Twitter. Developers which are developing the service are operationally responsible for a service being up and running. So I think this is a really good thing, because I think this is what pushes good developers to be the great developers, but it's not really the fun thing to do all the time. And I definitely know it's not, our spouses don't really like it all the time. For example, my wife sometimes when I'm on call, she tells me to go on a couch. And one colleague, his wife actually tells to his kids, you know, your dad is going to be on call. And they were like, oh, no, no. But this is why we also invested a lot in having a good monitoring of our system, and also in trying to automate and make our system auto-recover, auto-heal in many of the failure cases we could think of. Since we're having so many event types flowing through our system, we wanted to have a stricter control. What is it going to be delivered? This is why we ask all of our customers to define which events they want to be delivered, and the events which are not defined as they want to be delivered are completely filtered out. We wanted to do this so we would not waste resources on the events that we know are never going to be looked at. And finally, we designed our event delivery system to deliver 100% of data. We acknowledged that there is many different event types flowing to our system, and they have different loss requirements, but we felt that designing a system to do a single thing and do that thing well is much easier than actually having many more use cases. Since through our event delivery system we're delivering really important events, we use that as a less common denominator and, well, just designed our system not to lose any data. But designing a system to not do that or not do something is not good enough. This is why we also needed to build a monitoring service on top, which is tracking all the outputs and all the inputs, and based on that, it determines if we have any loss or not. The similar way we have timeliness SLA, we also have a completeness SLA, and in case the SLA is broken, we also have an incident process, and we're having a process how to communicate this to our customers. Sorry. So, in order for our system to be running 24/7 and for us to keep up with the SLAs, having a good monitoring is a must. With our system, we actually recognize that there are 3 different types of monitoring. We're having system monitoring for monitoring the general health of the system. We're having data monitoring for monitoring our timeliness SLAs. And we're also having a data loss monitoring for monitoring our completeness SLAs. We do system monitoring of our event delivery system exactly the same way like we monitor any of our backend systems. Here, what I want to point out is that even if the event delivery system is just a big box on this slide, it is actually a complex distributed system with many microservices which are working together to do the same goal. We're having a system monitoring on each of those components, and we're also monitoring the third-party services we're using in our system. We're monitoring CPU, we're monitoring memory, we're monitoring everything we could think of. We think the monitoring is really important because it allows us to see what parts of the system needs optimizing, and also in case of incidents, it's really easy to pinpoint the actual problem. But no matter how good this monitoring is, it doesn't actually allow us to see what our customers see and what our customers need. With this system monitoring, we're not actually monitoring the data which is being delivered. That means that sometimes we could have some really obscure bugs which would stop delivering the data even if the health of the system was good enough. Or it was, well, not breaking any SLAs or not triggering any alarms. So this is why in Spotify we came up with a data monitoring tool. Unfortunately, it's still not open source. But what the Datamon does is that it actually allows us, it shows us what is actually being happening on the actual storage. Every bucket you see here on the right is the actual hourly bucket of data being delivered. It can monitor data on cloud storage, it can monitor data on BigQuery, Hive, I saw even on Data Store, and I even saw it can monitor data on SFTP. Not really sure who uses SFTP, but well, it can do that too. Interesting aspect of the system, in order to actually allows us to be on call and keep up to our timeliness SLA, we can set the alarms and we can track historically how did we keep up with the SLAs. It does have other features, like we can look at the counters, we can go and drill down and see the resource manager and a bunch of other different interesting stuff. Datamon is definitely one of my favorite tools in Spotify, and I think it was one of the big game changers on how do we do ops in a data infrastructure. And finally, in order to monitor the completeness SLA, we built a custom tailored system which is actually monitoring all the outputs and all the inputs, and then based on that calculates if we did break the SLA or not, dumps everything to Elasticsearch, and from there we actually just graph it with Kibana. So what this system does is that it actually, if it detects that we did over-delivery or under-delivery of our data, it opens up a Jira ticket and it sends us an alarm. After that, we have a process, we start working on it. So in this example, on this slide, you can actually see what does it do. So we had over-delivery for a event, and then it actually opened up a Jira ticket for us that we can actually monitor how many Jira tickets did we get, and then we took all the things we needed to do in order to mitigate this issue. Let's talk about scaling a bit. Scaling is fun. I mean, everybody likes it. Today, Spotify is having 100 million monthly active users. We recently also announced that we have 50 million paying subscribers. All of those users are generating 1.5 million events per second in a peak hours, which actually translates to more than 60 terabytes of data delivered every single day. All that load is being split across more than 250 unique event types we're having in Spotify. This gives us a lot of interesting engineering challenges to work with, and we came up with an interesting design. But before we started tackling the hard technical issues, we also wanted to tackle a hard soft issue. Today, in Spotify, we're not seeing a rapid growth of the number of users we're having. We're also seeing a growth of developers which are starting to work with data. In order to make their life easier, we wanted to introduce a concept of ownership of the events. Ownership in this context means that the owner of the event is responsible for the quality of the event that is being produced, and it's also responsible of providing a good guidelines of how the event is going to be used. Then everything goes through a distributed configuration service, so the users of the event can actually go and track down who is the owner, so they can go and talk to them and figure out what to do with the event. Owners should not care about timeliness, and the owner should not care about completeness, because this is what we as event delivery team guarantee with our SLAs. One other aspect that the owners need to do, they also need to decide where do they want data to be delivered. By default, it's always being delivered to the cloud storage, but the owner can choose for data to be delivered to the BigQuery, it can choose for data to be delivered on Hadoop, and finally can choose for data to be delivered to Hive. So, since we have many event types flowing through our system, we wanted to actually split them and consume them by a separate parts of the system. We wanted to do this since we felt that writing many smaller parts of the system and managing this is going to be much easier than having one huge component that consumes all the events from one huge stream. This allows us to have a better visibility on how each event is performing and actually understand what the event is doing. But of course, it does have its drawbacks. So the first drawback is that by doing this and splitting our event delivery system and all the events to the independent streams is that we have more administration overhead. So this is why we needed to go and build a system which is going to talk to the compute engine and order the infrastructure needed for each of the events to be delivered. The next issue with this kind of setup is that determining the amount of machines which are actually needed for each event to be delivered gets a bit more complex. So our first stab on it was to actually have the same amount of machines serving every event we're having in Spotify. But of course, this had a big drawback. If we would use the same amount of machines for all the events, in case of the smaller events, we would waste many resources. In the case of the big events, there is no guarantee that we're going to be able to scale up and pick up the sudden spikes of the events being published. Of course, a fix of this that we wanted to avoid at all costs is to do the manual allocation of capacity for each of the events, or to push this manual capacity allocation to any of our customers. But, of course, we're lazy, we don't like manual work, and our customers definitely don't like manual work, so we wanted to give Autoscaler a try. Since we're already ordering machines on the compute engine, turning on the autoscaler was quite simple. You just say, this is the metric I want you to look at when you want to decide if you should autoscale something or not. This is the target that I want you to keep, and this is the minimum and maximum of machines that I want you to use. We decided to use a CPU-based metric since this seemed like a simplest solution, and we just wanted to see how it's going to work, and then iterate on it if it does not work. But first thing first, one important thing that needs to be considered before the autoscaler is turned on is that the components which are being autoscaled need to be stateless. If the components are not stateless, turning on the autoscaler is hard, or I would even dare to say it's impossible. The good thing is that we in Spotify started designing and building all of our services to be stateless long before we started considering the autoscaler. We did this because by having your services stateless, it's much easier to understand what are they doing, and it's also much easier to scale because you can just drop more capacity as needed. In case of hardware issues, you don't care. You just recycle a machine and order a new one, and that's it. The hard stuff, the state keeping, we usually try to push to the third-party services, which are battle tested and which we know that can handle the load. So in this case, in our event delivery system, we're using Cloud SQL, and also we're using Cloud PubSub. Worth mentioning here is that the Cloud PubSub, difference between Kafka and Cloud PubSub is that with the Cloud PubSub, you can get completely stateless consumers, and there is no limitation on how many consumers you can have. You just drop consumers in your system, and they just, well, somehow magically coordinate and consume the right messages. This fact that we can get stateless consumers was one of the biggest reasons why did we choose to use Cloud PubSub for managing all the streams we're having instead of Kafka. So we turned on the auto-scaling, and well, at some point, we noticed a really interesting thing. Sometimes we would have some machines using 100% of the CPU, while other machines from the same group would use 0% of the CPU because they ended up somehow in a zombie state. What was really mind-blowing for us and a bit unexpected was, well, the autoscaler thinks that the average usage of the CPU in this case is 50%. And then, because we wanted to save resources, and of course we wanted to have our machines use more than 50% of the CPU, we wouldn't scale up, even if the backlog was growing on the other side. The same situation would be if we would have only one machine. That machine's ended up in the zombie state. It does have 0% CPU. Autoscaler thinks, well, you're not using enough CPU, so I'm not going to give you more machines, and the backlog grows on the other side. Of course, we get waken up on the night, we need to fix this, and at some point, I guess, it got really hard, we got really frustrated, and we said this is a really important problem. We need to see how are we going to mitigate this. So first mitigation, the simplest possible ever, just always use at least 2 machines per each event type. This would avoid of actually getting in a really bad state. We could still end up in a bad state though. But because this mitigation alone wasn't enough, we needed to actually go and find another mitigation. How are we going to figure out which machines are in the zombie state and why are they ending up in the zombie state? But before I actually reveal to you what was the second mitigation, I need to explain what is being run on each machine which is being provisioned for a worker to run. So the first thing, we provision a machine. It's a completely blank machine, and then we start running Puppet. When the Puppet runs, it needs to install all the packages we need and to spin up all the services we need so the machine would end up in an operational state. So in our case, it installs Docker, it installs a deployment agent, it installs a service discovery configuration, and it installs a monitoring daemon. Once they're installed, our deployment agents take over and deploys our code to run on Docker, and our, well, worker starts serving the data. First, this process is really slow. It can take sometimes more than 10 minutes just to bootstrap a single machine. Okay? But not only being slow, this process is also wasting too many of our resources. All of the additional processes beside our, that are run there beside our worker are eating the same CPU and they're eating the same memory that our worker should use. This is actually limiting how small machine can be used for each worker. We need to use at least 4 CPU machines because we need 2 CPU for all the overhead we're having. I guess by now you're all wondering, like, why did you went with this process? How did you even come up with that process? Well, worth noting is that the Spotify just recently, and that was I think almost exactly a year ago when we announced it, decided to go in a cloud game. This is a process which we have been using to bootstrap all of machines in our data center. We've been using it for years. It does have, it is slow. It does eat a lot of CPU, but it works. There is a lot of operational knowledge being embedded in many of the Puppet manifests and in many of the Puppet classes, and how do we install Docker and all that kind of stuff. Since we are the first team in Spotify using the autoscaler, we were afraid of actually needing to reinvent this process, and we just wanted to use this as something simplest that can get us forward to see if the autoscaler is going to work for us or not. And of course, there is one thing that I also forgot to mention, which is creating a worse resource usage than it should, is that our deployment agent can deploy only a single worker process on a single machine, because it doesn't support multi-tenancy, and it doesn't support multi-tenancy with the resource isolation. Since this process is as complex, our first suspect was that the bootstrapping process is actually creating our zombie machines. And of course, the first suspect for the bootstrapping process was Puppet. Nobody likes Puppet. It is magical, and people are often just frustrated by it. So just blame Puppet. But even if we all like to blame Puppet, as we did, the truth was Puppet was working fairly well. All the processes were installed as they should, and all the services were going up as they should. So the other thing that when we started looking even further, we figured out Docker is the main root cause of all of our problems. It was like, it's like the hippest technology ever, and everybody is talking about Docker, and it's just terrible. And then that's why I put it like here. It's like it's constantly on fire, and it's all constantly sad because it knows that we're getting woken up, and our spouses get woken up and get angry at us. So there was like just so many crazy issues. So we would get like Docker proxy being broken, networking doesn't work. We would get Docker getting in defunct state, and we can only reboot machine to keep on working. And sometimes it pulls the image 100%, but then just returns 404, and then the only restarting Docker would work. Since we're not Go engineers, and since we don't want to go into actually understanding how the Docker works, because it should be just a black box, we wanted to find a workaround that would work best for us and enable us to move forward. So the first thing here was that we enabled health checks from the autoscaler. What the health checks do is that they are actually pinging our worker process, and if the worker process don't respond for a certain amount of time, they just recycle the machine. But here is a new problem. When they recycle the machine, they spin up a new machine with the same name, which now makes our Puppet sad. Puppet gets a new key, Puppet master has the old key, Puppet cannot bootstrap machine, and we just get in a worse state. Okay, we can't use health checks. Let's see what else can we do. Kill scripts. So what we did is actually we used Puppet to help us with disciplining Docker. So we have a kill scripts which are looking at the Docker state, and then based on that, they wipe the Docker state and restart it, or just reboot the machine. We put a monitoring, because we like put monitoring, to understand what is happening in our system. And what we saw, it was terrifying. We get 10% of all of our machines being rebooted every hour because Docker is ending up in the defunct state. If the Docker is defunct state, our machine cannot work. Like, oh. The important thing is that it allows us to move forward, and no matter how terrible it is, we're not woken up, and our SLAs are safe. So let's look at the graphs. How are we actually performing with autoscaling? So on the top graph, you can see the amount of events which are being published. You can see that the peaks are really prominent, while there is like huge dips. Here is how many machines are we using. You can see there are some peaks, but they're not as prominent. So the good thing about this process is that we actually prove to ourselves that we can save some of the resources during the day, during the night, not during the day. But the problem was that because of all the suboptimal resource usage, the fact that we have a container orchestrator which doesn't support multi-tenancy, and the fact that at least we need 2 machines to be used, there is a lot of resources still being wasted. And this is definitely something that we want to look at. Okay. So now it's the fun stuff. Let's see. So how many of you like horror stories? Come on, okay, I can skip this slide and just go to some boring stuff. So this is one of the war stories, and I think this is something that you should teach in schools, and this is something that you should say, like, maybe write a warning with the autoscaler, like you write warnings today when you buy alcohol bottles and stuff, alcohol. The thing is, autoscaler is really powerful, but you need to be really careful how are you using it. So what our system does is that it consumes from the cloud PubSub, it writes to the cloud storage. So here is PubSub, here is cloud storage, and it persists some state to the data store. Once that state is safely persisted, it just sends acknowledgements back to the cloud PubSub. Okay, we start pushing more and more events. Our system, well, was growing, and at some point, data store caught fire. There are some internal limitations which are, well, not really scaling well the way we designed our software, and it became increasingly sluggish. As it became sluggish, we were not sending acknowledgements back. Our backlog grew. We started using more CPU. Autoscaler dropped more machines. Here is more machines, so you can consume your backlog faster. Okay. We put even more pressure to data store. Our backlog grows even more because data store just goes in a worse state. Autoscaler just says, here you go, here's more machines. Let's see how we're going to deal with it. So what do you think happened next? So what happened is that we scaled until we could use all the available RAM in the project. All of a sudden, we were having lunch, and all of a sudden, people actually call us, like, why do you need a terabytes of RAM? Like, are you insane? People could not spin up their data flow jobs. People could not spin up data pro cluster. People could not spin up machines to serve the service. All in all, it was a really fun night. I was actually on call during that day, and I think I went home at around 1 or something like that, and was like completely tired. I was like, ah. But nevertheless, it was a good learning opportunity. And then after we did a postmortem, we kind of talked about it, and it turns out we could actually avoid this, but just being smarter about handling our failure cases. If we had a simple exponential backoff in case we cannot write to the data store or maybe to cloud storage, we would throttle down the CPU because we would have, well, more time before we consume from the PubSub. And the other learning was, well, data store in this case was not the perfect tool for us to use, so we started using Cloud SQL. All in all, because the biggest problem with this approach is that we're having really suboptimal resource usage, and we're trying to figure out how to work with it. So we started looking closely to Kubernetes, because Kubernetes comes as a managed product from the Google Cloud. It also supports autoscaling out of the box, and it supports multi-tenancy with the resource isolation, everything we need. But unfortunately, not everything is simple for us, because if we lose the ability to run Puppet on the machines, as we would lose it if we would use managed Kubernetes, we would not be able to do the monitoring we do it today, and we would not be able to do the service discovery, which we do today. But we'll see. We'll see what the time is going to show. And then I have just a few words before I end on how do we do testing. In Spotify, we are taking testing seriously, and we are big fans of doing continuous integration and deployments. So what we do is that for many of our backend services, we always ensure there is enough unit tests to be tested before they're being pushed to the production. But because Spotify event delivery system is a complex distributed system consisting of many smaller microservices, we wanted to have a end-to-end test, which is going to cover the full flow and which can be run on a single developer machine, so it would be easy to iterate on it. So what we did, we actually just, stuffed all the stuff in a single Cucumber file. We have all of our services being spinned up as a black boxes on Docker, introduce some input, and observe the output, and that's it. Interesting thing is that this is run before the code is being merged, and it's also being run before the code is being deployed to production. And few times, we actually ignored what the end-to-end test is telling us, because sometimes it can take up to 10 minutes to run, and we had big incidents, but when we learned, it actually saved us quite a few times. And that would be it. Thank you. So before we start with the questioning, we are hiring. If you like working with these interesting problems, feel free to check the site. And please don't ask me any questions about the Google Cloud costs. And now questions.
Yeah, what went wrong with Kafka, actually?
So with Kafka went wrong many things. So the first thing that went wrong is that we're having multiple data centers, and we wanted to use the mirror makers. At a point when we started to actually experiment with the mirror makers, we figured out that mirror makers are not really mirroring the data, they're dropping the data if the destination cluster is down. So that was like really big thing. The second thing that went wrong is that the client libraries were kind of hard to work with because they were ending up in a really weird states that we didn't know how to recover from, and the only thing was to reboot the machines. And at that point we said, yeah, just Cloud PubSub is just more convenient for us.
Okay, thanks.
Okay?
Yeah. Hi. I have a question regarding having the teams doing operations of your services. So do you have any metrics regarding, I don't know, frequency or severity of incidents, maybe compared to other players of your scale or to the time before you switched to that mode?
So I don't have the numbers because we don't really track them. I mean, we do have incidents across the board every single day. Or maybe not every single day, maybe every second day. Yeah? But the important thing, what actually changed for us and why did we went with the actually DevOps system is that we were hiring more and more developers, and that happened a few years ago, and we were not hiring, or we couldn't hire enough SREs. So this is why we pushed more operational responsibility toward the squads. So what I think is that you, as a developer, when you're developing and when you're seeing your system in production, you're inclined to make your system much better because you care much more about the people you work with than just some operations team that sits like 3 rooms down or something like that. And I think that's what works the best. And I really think it works really well for us.
If you can just back down one slide, please, from the testing. Yeah. Do you run this on the developer's machine? Everyone runs this on their own PC?
No, but why I said it's a developer machine is that because I think if you can run your stuff on your developer machine, it's much easier to iterate and fix it. So we were having issues with Python in the beginning, and the biggest issue was the developers could not run the Python and the libraries we developed on their local machines. But what is important, like even if it can run on the developer machine, we don't really run it that. We have a Jenkins server which is handling all our builds and all our deployments, and this is where this is being run.
So in a CI environment?
In a CI environment, yes.
Because the question is, when you have many microservices that you work on and small teams working on each one of them, then you have many dependencies. So the question is, when you work on just one, and you want to test what you are doing, then you require all the others to be up in a way.
So I guess this is a bit specific. We are having a big system that we need to maintain, and we just happen to think it's just easier to cut it in many smaller pieces. But the important thing is that every team has its own Jenkins, and every team decides how it's testing its own microservices. So in Spotify, we have many microservices, but there is no overall end-to-end test. How are they being tested? Because it is hard, and it requires so much communication and so much like effort for this to work. And of course, it doesn't work ever. So yeah.
Okay, thank you.
Okay.
Hi there, sorry. A question I had was related to the Docker. Sorry, I'm over here.
Okay.
The Docker percentage failures. It seems incredibly high, and I was wondering, could you give us some more information as to the type of failures you saw? And are you happy to continue to live with that level of failure? And if not, what are you doing to try and address it?
So I can tell you we're definitely not happy, and I hate it so much. Currently, we're working with one team in New York, which is handling the Docker stuff, and we're trying to upgrade. But of course, this is not simple because the upgrades have other bugs, and like it's kind of, I don't know. But the thing is, like, we think that the Dockers and the containers were a big game changer for us. And then we would definitely like to keep on working with the container environments as we are working today, but we don't know what would be used. That's the problem. Huh? We had a big incident a while ago with Kubernetes, and one of my questions was like, can we use something else, not Docker, for Kubernetes? And then some Google engineers said like, please, please, please ask our PM to support Rocket. Apparently Rocket is much better, but I have no idea, so I don't know.
I mean, a lot of the Google services are based on Kubernetes themselves, so if you have Google engineers telling you not to use it, that doesn't inspire confidence going forward with it.
So the fun thing was like, okay, so we were building our own scheduler on Kubernetes to schedule all the data jobs, and it has a special quirk. It actually wants to run backup jobs. So at some point, we started having a lot of failures because Docker PS was taking more than 60 seconds to return. And then when we started talking about the Kubernetes engineers while trying to solve the case, they were just mentioning that there is so many workarounds they needed to implement for the Docker, and they were so scared for going from one version to another because if they would go, probably Docker PS would be faster, but who knows what else would they actually unleash. So I don't know. I mean, it's kind of hard.
The expression "oh dear" comes to mind.
Yeah. Okay.
Hi, over here.
Yep.
Thanks for the talk. So you mentioned you've got something like 250 event types. How do you split this into pub subs? Do you have like dedicated topics per event?
Yes. So I did this talk before. I know when I talked to Danny, he said I should show you, but I was afraid this is going to confuse so many people. So, because it is confusing, and it's actually 40 minutes talk. So we have we're sending a single stream of the events because of the legacy reason to this service, and then we're splitting them up and publishing them to the topics. Another quirk of PubSub is that actually the topic is not the same as topic in Kafka, so you actually need to create a subscription, and every subscription you create, it has own state. So every event which is being consumed by our events here is consuming data from a specific subscription.
Do you find you get duplications as well, say from the same topic, if you've got multiple workers on one subscriber? And how do you deal with that? So
here is, again, that was part of the bigger talk. Oops, sorry. Yeah, I'm sorry, I can't. No. So the thing is like, yes, Cloud PubSub is at least once. So what it does, it actually consumes it and writes it to the temporary bucket. And then saves, state saving here is actually ensuring us to say, this is when the bucket is complete, and this is when you should start processing. And then at the end here, we have a MapReduce job, which is taking all the intermediate files and then dedups them. And then this is not enough. So some of the events can be reached right from the clients here, and then be retried. So because we're having a not client timestamp, we're actually having a syslog timestamp, we're actually just dedupping on our semantic. But at the other end here, there is another job which is doing a semantic dedupping, so we would ensure that the messages are really dedupped even from the client perspective.
Okay, thank you.
Okay.
Last question.
Hi there. So you mentioned you have this configuration service where the event type owners can decide whether they want you to even consume their event type.
Yeah.
Of your 250 or however many you have, how many are actually being processed and how many are you just throwing away? And are you literally throwing them away so they're never recoverable, or is there some of these storing them somewhere? And finally, if I may, since you've been running Cloud Pub Sub, have you ever lost data?
So no, we haven't lost data with Cloud Pub Sub, and I'm personally most happy with the Cloud Pub Sub from all the Google Cloud services we're using. And in order to save resources, we are completely dropping them. And we communicated this really clearly. If you're not doing your due diligence, you're not going to get your events, and they're not recoverable. Well, truth is, they're still recoverable because we do have stored them on the syslog files for 3 days, but we just pretend they're not, so that's it.
Thanks, everyone. You can still come here to ask questions if you want to.
All questions except the pricing.